Welcome to the solutions to homework set number 1 for ECE 320. Now, in this homework set, it's just a review of circuits 1. One of the problems you should be able to do is solve for this. What is the net impedance between A and B? To do that, you need to use resistors in series and parallel with complex numbers. This is where I really recommend the HP calculators. HPs give the right answer, and they handle complex numbers just fine. They're a little bit odd. There is no equals button. They use a stack. So when I add, subtract, multiply, and divide, I'm using the stack. So you first have to set up the stack, then you execute it. If you're taking embedded systems, these are like registers. When I add, subtract, multiply, and divide, they operate on the registers. So first I have to set up the registers. For example, 5 plus 6, I would do 5, enter, 6. 5 and 6 is on the stack. I can now add. To multiply by 7, I hit 7. That automatically pushes 11 up on the stack. I now have 7 and 11. Multiply. Answer 77. Divide by 13, and so on. Oops. For complex numbers, you have this complex key. I do like 2, enter 5, complex. That's 2 plus J5. 9, enter 3, complex. And now you can add, subtract, multiply, and divide complex numbers. A second mode is if we go to polar, I can say 5 at 45 degrees plus 6 at 13 degrees. So set the two numbers on the stack, and now we can add them. I personally prefer rectangular mode. So anyway, back to this problem. I've got 400 ohms in parallel with J400. In parallel, the inverses add. So I'll take 400, inverse, J400, that's 0, enter 400, complex. There's J400, take the inverse, add the inverses, and invert. So this is 200 plus J200 ohms. In series with 30, in series they add. In parallel the inverses add. So take the inverse, minus J200, 0, enter, negative 200, complex, there's minus J200, take its inverse, the inverses add, 300, inverse, add. Once I get the sum of the inverses, invert. So all this together is 138 minus J68 ohms plus 60. So there's your answer. Again, I highly recommend getting a calculator that can do complex numbers. You need them on tests. I'm serious when I say the HP calculator is worth 10 points on a midterm. It can do these calculations with ease. The TIs really struggle, Casios really struggle. You need a calculator that does complex numbers. That's the HP. Hewlett-Packard is really a company made up of electrical engineers, and not surprisingly, they build really good calculators for electrical engineers. So there's the first problem. Second problem. Find this net impedance. Again, going right to left, I would say plus J400 minus J800 is minus J400. Yeah, that I can do in my head. In parallel with minus J700. That I can't do in my head. So take the inverse, 0, enter, negative 700, complex. There's the minus J700, inverse. In parallel, the inverses add. So all this together is minus J254 ohms. In series with 300, in series they add. In parallel it's the inverse. So take that inverse, take 0, enter, negative 600, complex. There's minus J600, inverse. Add the inverses. So this is now 131 minus J224 ohms, plus J200. In parallel, take the inverse, 0, enter, negative 500, complex, minus J500, take the inverse, add them, plus 100. So there's your answer, 212 minus J51 ohms. And again, the reason I push the HP calculators is they work really fast. Time is worth points on a midterm. Midterms tend to be a race. Get to the answer. HPs will dust any other calculator. And getting the right answer is also worth points. HPs give you the right answer. So again, I really push the HPs. Other faculty push other calculators, but I'm the one that's right. It's really your choice. Pick a calculator, whatever works for you, but make sure it works because it's worth points on tests. Problem number 3, voltage nodes. Write the node equations for the following circuit and solve. First, start with the node equations. On the quiz on next Friday, what I'll probably do is ask you to write the node equations, and that's it. On the homework set, you can solve, but on the quiz, I don't assume you have access to MATLAB. And really, if you do have MATLAB, once you get the equations right, solving them is pretty straightforward. The important thing is to get the equations right. So anyway, I've got 3 nodes. I need 3 equations for 3 unknowns. The first equation is a gimme. The voltage source says that V3 minus V2 is 5. So there's one equation, the first one. Second equation, take the node equation right here. Current up plus current down plus current right has to add to 0. Current up is V1 minus V3 over 100, right here. Current down is V1 over 200, and the current right is minus 40 milliamps. Those have to add to 0. Now I'm stuck. I can't write the node equation V2 because I have no idea what this current is. I can't write the node equation V3 because I have no idea what that current is. That's when you get a supernode. It's a closed path where I know the current coming out of that node. Here's one option. There's other options as well. But if I choose that as my supernode, then the total current coming out of that node has got to be 0. So that total current will be the current left, current down, current up and left, current up and right. So it should have 5 terms. Current left is 40 milliamps. Current down is V2 over 300. Current down is V3 over 400. Current left is V3 minus V1 over 100. And current right is V3 over 500. So now I've got 3 equations, 3 unknowns. To solve, what I do is I group the terms. So pull out the V1, gives you 1 over 200 plus 1 over 100 V1 minus 1 over 100 V3 is 40 milliamps. Group all the terms together here. I get minus 1 over 100 V1 plus 1 over 300 V2 plus 1 over 100 plus 1 over 400 plus 1 over 500 V3. 3 equations, 3 unknowns. Now put that in matrix form. In matrix form, I'll have my unknowns, V1, V2, V3. The first column is times V1. So I just kind of make a note to myself. This kind of helps when I write it out. First equation is V3 minus V2 is 5. Second equation, 1 over 200 V1, 1 over 200 plus 1 over 100 V1 minus 1 over 100 V3 is 40 milliamps. And the last equation, minus 1 over 100 V1 plus 1 over 300 V2 plus this mess times V3 is minus 40 milliamps. Throw that in MATLAB in matrix form. Here's calling this A, call this B. Then the voltage is the inverse of A times B. So that should be my voltage. To check my answer, I can throw that in Circuit Lab and see what the voltages are. And 2.86 minus 4.70, 2.86 minus 4.70, same answer. That's problem number 3. Problem 4 is using current loops. Solve. With current loops, I've got 4 loops, so I need 4 equations, 4 unknowns. Start with the easy equation. Easy equation is right here. The current source says the current left is 40 milliamps. The current left is I1 minus I2. So there's my first equation. I can't do the loop equation around I1 because I don't know what this voltage is. I can't do I2 because, again, I don't know this voltage. I can do I3. Around loop I3, if I start right here, I get 300 times I3 minus I2, that's the current going up, minus 5, plus 400, I3 minus I4, back where I started, equals 0. And kind of a check. All the I3s should be positive, everyone else is negative. Around loop I4, starting right here, 400, I4 minus I3, plus 500 I4, back where I started, equals 0. I need one more equation. That's a super loop. Here's one possible super loop. And kind of, if I look at the resistors on these equations, I've got the current source, that's my first equation, the 300 ohm, 5 volts, 400 ohm, and 500 ohm. All those appear in the equations. The 100 and 200 don't appear yet. They do affect the circuit. So my fourth equation should include the 100 and 200 and not pass through the 40 milliamp source because I don't know that voltage. Here's one valid solution, and there's others. So that'd be going up 200 I2 plus 100 I1 plus 500 I4, back where I started, equals 0. 4 equations, 4 unknowns. To solve, I can group the terms, put it in matrix form, throw it in MATLAB. Here's my A, there's my B. Solve, there's the current in amps, or times 1,000. There's the current in milliamps. I1, I2, I3, I4. In Circuit Lab, if I click on that resistor right here, that'll tell me this current, that's I1. Click right here, that'll tell me the current going up, that's I2. Click right here, current going down, that's I4. I3 I can't really get. I can do this guy right here. That'd be this current, that's I3 minus I4. But you could calculate or just figure, if I have I1, I2, I4 correct, probably I3 is correct too. So what I should get is 25.6 milliamps minus 14.3 milliamps, something something. 25.6 milliamps minus 14.3 milliamps, something something. Did it right. The last problem is solve for V2. This is where I use superposition. Superposition is where I use linearity. Linearity says f of a plus b is f of a plus f of b. I have two terms, an AC and a DC term. Treat that as two separate problems. Solve when the input is 10, that's in blue. Solve when the input is 4 sine of 6 under t, that's in red. Take the two answers, add them up. Starting out in blue, if the input is 10, then my representation of V1 is just 10, so 10 represents 10 volts. Kind of like duh. Inductors don't matter DC, that's j omega L, omega 0. Capacitors don't matter DC, this is 1 over j omega C, or infinity. If the current is 0, ignore it. So by voltage division, I get 120 over 15 plus 120 times 10. V2 is 8.889 volts. That's the DC term. Now the AC term, that's in red. Here's the input. My input is 0 minus J4, 0 cosine, 4 sine. Omega 600, J omega L is J390, that's the inductor. 1 over J omega C is 1 over J times 20 microfarads times 600. You can kind of do it this way. I forgot, 600 radians per second times 20 microfarads, 20 e minus 6. Take the inverse, that's 83.3 ohms, and 1 over j is equal to minus j. Multiply the top and bottom by j, I get j over j squared is minus 1, minus j 83.33. Now, use voltage division. I put these two in parallel, so let's do that. 120 ohms minus j 83 inverse, add inverse. This is 39 minus J56 ohms. Voltage division, R1 over R1 plus R2. So hit enter twice, or 3 times. That makes a couple copies. Add 15 plus J90, complex. There's the R1, R2, add them together. There's the denominator polynomial, or denominator, there's the numerator. That's why I hit enter like 3 times, make a couple copies. Take the ratio. That times the input. 0, enter, -4. There's my output. 0.56 plus J0.58. What that means is 0.56 is cosine minus J is sine. So there's B2 of t for the AC term. Total answer is DC plus AC. And Circuit Lab I can check. Let's see. If I build this circuit, double click on this, the DC term is 10 volts. The AC term was 4 volts peak. Frequency is 600 radians per second, which divided by 2 pi, 95.49 hertz. Inductor, capacitor, simulate. When I simulated it for a couple cycles. This is 95 hertz, so 3 cycles is roughly 300 milliseconds. So it's down there. Here's the input. This is V1. This is your V2. If I measure the peak, the maximum, and the minimum, that'll tell you the DC and the AC terms. The DC is the average of the maximum and the minimum. The AC is the difference between the two. And here the units are peak to peak. You gotta label the answers. Peak is what you calculated in problem 2, ground to peak. RMS is what an ohm meter reads. Peak to peak is on the oscilloscope, peak to peak. They're all related, but they're different. This actually matches the calculations. Take this, the magnitude, that's 0.8 volts peak, that's your VP. Twice that is peak to peak, 1.62, 1.608, they match. So you got to compare the peak to peak. When you compare, make sure you're comparing the same numbers, same units. What I calculate is pretty much what I got in Circuit Lab. So that is homework set number 1 for ECE 320.